Welcome to the Crazy Hat Chemist. So another video here on Thermochemistry Part 2. So let's get moving with this next video. Bam! So today we are talking about the entropy change of a system, calculation number 2. So we're going to calculate the entropy change of a system for the combustion of ethanol, given the partial table of thermodynamic values at 25 degrees Celsius, or in other words, that's 298.15 Kelvin. So the first thing that we need to do is we need to figure out what the formula for ethanol is. And I don't know if you remember, way back to organic chemistry, that's meth, eth, prop, and then butyl. And then after that, it goes by the prefixes of pentane, hexane, heptane, octane, nonane, and decane. Okay, so, but this is the second one. So it's meth and then eth. So F, that means that there are 2 carbons because it's the second one in line. Okay, so what I want you to do is I want you to draw 2 carbons. 1 carbon, second carbon. Okay, and then put a single bond between those 2 carbons. Now, at each of those carbons, since each of the carbons form 4 different bonds, that means that we need a total of the rest of the bonds to be hydrogens in this case. So you're going to have 2 carbons, and then you're going to spread around those 2 carbons the appropriate number of hydrogens such that carbon has 4 different bonds. And how many carbons would that be? That would be 6 carbons. So you should have C2H6. Okay, so that would be ethane. That would be ethane, so that's a single bond. But this is ethanol. So the OL ending indicates that this is an alcohol. And for an alcohol, the OL ending indicating an alcohol is an OH group. So what you're going to do is you're going to replace one of those hydrogens, take it off, in other words, replace it with an OH group. So now you're going to have C2H5OH. All right, that is the formula for ethanol. Now, it says that this is a combustion reaction with ethanol. So what I want you to do is I want you to write the balanced equation for the combustion of ethanol. Now, we do know that ethanol is a liquid, but it can be in the gaseous state as well. I've found this value in the table as a gaseous ethanol. So that's what we're going to use. So we're going to use the combustion of ethanol. So combustion of ethanol, remember, C2H5OH. Now what you're going to do is write the rest of that combustion reaction, and then you're going to balance it. So I want you to pause the video here and then restart it once you've written the balanced equation. Okay, so hopefully you've written the balanced equation for the combustion of ethanol. And that is going to be ethanol, C2H5OH, with oxygen will produce carbon dioxide and water. That is any combustion reaction. And that is right there. So that's C2H5OH gaseous plus 3 moles of oxygen, molecular oxygen, that's gaseous. There's the arrow, and there's that delta sign above the arrow indicating that this reaction requires a little bit of energy for it to start off, either a lit match, a spark, or something like that, but it is producing energy. And on the product side, you have 2 moles of carbon dioxide and 3 moles of water in the gaseous state. So hopefully all those states of matter, hopefully the balancing worked out well for you as well. Now I want you to count how many moles of gas do you have on the reactant side. 1 mole of the ethanol and 3 moles of the oxygen. That's a total of 4 moles of gas on the reactant side. How many moles of gas do you have on the product side? I have 2 moles of carbon dioxide, 3 moles of water vapor. So that would be a total of 5 moles on the product side for gas. So you're going from 4 moles of gas to 5 moles of gas. That's an increase in the number of moles of gas. Now that should make sense because this is a combustion reaction, and combustion reactions are exothermic. That is an enthalpy change of negative. And since they are combustion reactions, and that would also indicate the 4 moles of gas going to 5 moles of gas, that this is more disorder. Now, let's see if we can verify this numerically by looking at the let's see if we can look at the data table and verify this information here. So I've got a partial data table of my thermodynamic values. I have all in the gaseous state, you should see. I have the ethanol at 282.70. I have the oxygen, molecular oxygen, at 205.07. I have the gaseous water at 188.84 and the carbon dioxide at 213.74. All of these S0 values have units of joules per Kelvin moles. Okay, so my basic equation that I'm plugging into here for the change in enthalpy of the system is going to be this. And that's delta S0 for the system is equal to the sum of the S0 for the products minus the sum of the S0 for the reactants. Now remember, the products are on the right-hand side and the reactants are on the left-hand side of that arrow. I plugged in some of that information here, so I got delta S0 of the system is equal to moles of carbon dioxide times those units, I'm indicating those units, plus the moles of water vapor times those units, minus the moles of the ethanol times the units, and plus the moles of oxygen times those units. Again, I want to emphasize, just like on the previous video, I want to emphasize the fact that molecular oxygen has an actual value. It's 205.07. And it is anything that we have in entropy has a value to it, unlike enthalpy, where you have elements in their standard state that are 0, but not with entropy. All right, so let's plug in the values with the moles and from the data table, and this is what we get. Delta S0 for the system is equal to 2 moles of carbon dioxide times 213.74 joules per Kelvin mole, plus 3 moles of oxygen, 3 moles of water times 188.84 joules per Kelvin mole, minus 1 mole of ethanol times 282.70 joules per Kelvin mole, plus 3 moles of oxygen gas times 205.07 joules per Kelvin mole. Once you plug all this information into your calculator, cancel out the units of moles, sum them up, you're going to have 2 decimal places in your answer. And here's my answer. Got delta S0 for the system as positive 96.09 joules per Kelvin. And again, this number should make sense here, because this positive sign indicates that there is an increase in the entropy. That is, there's less order on the product side than on the reactant side. Okay, and this is seen as there's an increase in the number of moles of gas from 4 to 5, as I aforementioned previously in this video here. Okay, all combustion reactions should be following the same process of being a positive delta S0 for the system. Okay, I am the Crazy Hat Chemist, and I got a great joke for you. This is an energy joke here for you. Okay, and hopefully you see that. We got a mom, we got a dad, and we got 2 kids. So what do you think this might be? Okay, what is the above diagram called? Gonna have to think about that. Scratch your head, scratch your temple. What is this diagram called? Well, it's called the family jewel, of course. That's just hilarious. You are laughing out loud, hopefully. Okay, make sure you add a comment in the comment section about that. It took me hours to make that slide and to come up with that joke. If you like that, give me a thumbs up. Subscribe to my YouTube channel. Please pass on my YouTube channel to all your favorite chemistry friends. And of course, I got a crazy hat. This hat is at least, I think, 18 to 19 years old. I got it from a set of cheerleaders who went to Disneyland for me. And of course that, and then the best part here is, whoa, look at that, chemistry. You gotta love that. Again, give me a thumbs up, subscribe to my YouTube channel, check me out on the web. You can see my website, and you can order yourself a sticker if you want, or even a t-shirt if you want. Sticker, t-shirt, get a sticker. See you next time. Talk to you later. Bye for now.